Hello, the objects that we'll be looking at here are curves and surfaces in 2 and 3 dimensional space, and they are primarily studied by means of parametrization. The main properties of these objects, which will be studied, are notions related to the shape. We will study tangents of curves and tangent spaces of surfaces, and the notion of curvature will be introduced. We will also be looking at the torsion of these curves and surfaces. These notions are defined through differentiation of the parametrization, and they are related to the first and second derivatives. Hopefully by the end, you should be familiar with the properties you might find associated with curves and surfaces, and thus be able to fully describe a curve or a surface.
This is the plane curve that we're going to study.
But first, we will introduce some new notions which we can use to study this curve.
What are the curvatures of these curves? Intuitively, we'd like to say that this curve has high curvature around here, but low curvature around here. But how can we measure this curvature precisely? One thing we've just pointed out is that the curvature of a curve is a local property of the curve, meaning it only depends on points which are close to the point. You may have previously met the idea that the tangent line to a curve is the best local approximation of the curve by a line, so perhaps we can measure the curvature in a similar way. What will happen if we try and approximate a curve by some other shape, say a circle? At this point where the curve is curving quite sharply, we have a small circle, whereas over here the curve is almost flat and we have a large circle. For this reason, we can define the curvature of the curve to be the reciprocal of the radius of the circle.
It turns out that there is a formula for the curvature in terms of the first and second derivatives of the curve. We also have to make sure that the derivative is not zero, since we are dividing by it. If the derivative is non-zero, the curve is called a regular curve. This formula is quite long and tedious to compute by hand, so maybe we can simplify it somehow. The idea behind this simplification is to find a different way to describe our curve called a reparametrization. Here are some examples of reparametrizations. As you can see, the curves are all the same length, but the speed of each one is different. This one is particularly nice because the speed is 1 unit at every point. In other words, the length of the first derivative is 1. After substituting and doing some algebra, our curvature formula changes from this to this, which is much simpler.
Another natural question we can ask is, how do we measure the length of the curve? How long would this part of the curve be if we stretched it out into a straight line? The first thing we could try is to approximate the curve by a straight line. This probably won't be very accurate, but we improve the approximation by splitting the curve into lots of small pieces and approximating each one by a line. If we take smaller and smaller pieces, the sequence of approximations will converge to the exact length of the curve. Unfortunately, the exact length can be difficult to compute because the calculation involves an integral. However, it's a very useful function to have when we can compute it. Since the inverse of this function is exactly what we need to compute the unit speed reparametrization, for our curve, the integral can be computed explicitly, but the inverse cannot be, so the unit speed reparametrization is hard to compute.
The next area to address is space curves, and in our example we have this curve. You find the properties that we have previously mentioned, the curvature, unit speed parametrization, arc length and regularity, in the exact same ways as you would for a plane curve. However, with space curves we can find an additional property, the torsion. The torsion is a measure of how fast a space curve is moving out of a plane and is given by the following formula. For the space curve presented here, we find that the torsion is 0. That is because the curve lies directly on top of a plane.
We can see that our space curve is a rotation of our plane curve.
The final thing left to talk about are surfaces. The surface we're going to discuss here is the following. One property that surfaces feature that curves don't is area. In order to find the area of a surface, we must first compute what is known as the first fundamental form. The first fundamental form is the restriction of the inner product to the tangent space. That is, it measures how much the tangent vectors point in the same direction. The first fundamental form allows us to compute distances and areas.
To find the arc length of a curve on a surface, you need to integrate the square root of the first fundamental form evaluated along the curve. You can also use the coefficients of the first fundamental form to compute the area of a region on the surface. If you consider the coefficients in their matrix representation, the area is the integral, the square root of the determinant of this matrix, integrated over the region.
The first fundamental form, together with the second fundamental form, allows us to compute the shape operator, which describes the curvature and shape of the surface. The shape operator is a matrix function whose eigenvalues describe the curvature of the surface in different directions. If the sum of these two values is 0, the surface is called a minimal surface. These surfaces have many interesting properties, most notably that the area of the surface is locally minimized. This means that the surfaces can appear in nature as soap films. Our surface, called the Shirk surface, also happens to be a minimal surface.
The animation here shows when we intersect our surface with a plane at certain points, this intersection is the same as our space curve, which, as we have previously mentioned, is also a rotation of our plane curve. So all of our given curves and our surface are connected. The study of minimal surfaces began in 1762 when Lagrange was looking at the problem of finding this surface. A surface of a least area stretched across a given closed contour. To solve his problem, he derived the Euler-Lagrange equation for the solution, but the only surface he could find to satisfy this was the plane. However, in 1776, Meusnier discovered that both the catenoid and the helicoid satisfied the equation. He also found that the differential expression corresponds to twice the mean curvature of the surface and concluded that surfaces with zero mean curvature are area minimizing. After this, in 1834, our surface, the Shirk surface, was discovered. Minimal surfaces continue to be studied today with expected applications within molecular engineering and materials science, and already play a role in general relativity.